Okay, and in 13.2 we just deal with some more power of a point problems. So we're going to do two more problems in this video, and they're pretty exciting. So in this first one, this is more of a numeric answer. So in the diagram, we want to show that, or we're given that BP is equal to 8, AB is equal to 10, CD is 7, and angle APC is 60 degrees. Okay, and we want to find the area of the circle. Okay, well at first glance this is like, okay, we give you all this information and we ask, is the sky blue? Well, okay, but how do we figure this out? How do we answer the question if the sky is blue? So what I need to do is, well, I recognize that the power of a point theorem applies here if I do AB, or A to B, and, or sorry, P to B, so that's 8, times the total length, which is 18, and that should be equal to 7 times, oh, and I think I labeled this wrong. Let's back up. CD is 7, so let's label that correctly here. And so if this is 7 and this is some unknown value, say k, then this is going to be a little bit different on the right side. I'll get k times k plus 7. And so then doing the math out, this is 144 is equal to k squared plus 7k. And so I get the quadratic k squared plus 7k minus 144 is equal to 0. And so factoring, I get this is k plus 16 times k minus 9 is equal to 0. And the only answer that I really care about is that the positive one, because I can't have a negative distance. So this is 9. Alright, and now what do I do with this? Well, now my diagram isn't the best diagram, but if I look at this, I note that this entire length here is 18. I know the angle measure here is 60. I know from P to C is 9. So if I were to, say, connect A to C, and again my diagram isn't that good, I would see, okay, well this is 60, this is 18, this is 9. This is smelling like a 30, 60, 90 triangle to me, because I see that the length of the shortest leg is, or the hypotenuse is twice the length of the shortest leg. So how do I know that though? Well, we can actually verify that by using similar triangles. Yes. Which I'll leave that up to you to show. But so if this is a 90-degree angle, then I know that this length would be 9 square root of 3. Okay. Still not helping me, because even though this looks like a diameter in my picture, in reality it isn't. And in fact, if I were to again draw a better diagram, I would get that A to D is actually a diameter. So imagine just taking this whole thing and shifting it. Maybe I can even do that. Not easily. So A to D is going to be a diameter. Okay, so now how do we find that? Well, I still know that this is a right triangle, and so that I can find this using the Pythagorean theorem, which I'll let you show, but this ends up being 2 times the square root of 73. Okay, so if the diameter is 2 square root of 73, then the radius is square root of 73, and then therefore area is equal to pi times the radius squared, 73 squared. So the area is just 73 pi. Okay, so that's the first example. The second example has to do with a circle and an equilateral triangle. So this construction is made so that AW is congruent to AY, and also we're given that the circle is tangent to side BC at point Q. Okay, and now with this, what we want to do is we want to show that, again, at the very, very end, that BQ is the same as QC. Okay, now to do that, we're going to need to employ the power of a point theorem several times. So first thing I can say is that AW, so the length of the left side here, AW times AX, is equal to AY times AZ, but I know that AW and AY are the same length, so what that gives me is that AX is equal to AZ. So I get that these segments are congruent. Okay, and then lastly, as a result, since the triangle ABC is equilateral, if these two parts are equal, then these remaining parts must be equal. Okay, so that helps out a great deal, but how is this gonna help me? So what I need to do is actually set up two more power of a point theorem equations. So I'm going to set up bx times bw is equal to bq times bc. So that's one equation. Then another one, I'm going to set up the one for vertex C. So cz times cy is equal to bq times, or sorry, not bq, cq. Try that again. cq times bc. Okay, now note that bx and cy, these two, are the same, as are bw and cy. So really what I can say is that as a result of all this, BQ times BC is equal to CQ times BC, and BC's cancel, so that means that BQ is equal to CQ. And as a result, I can say, therefore, Q is the midpoint. And so finally I got these line segments to be of equal length. Q is the midpoint of BC. Done. Okay, and so this one, again, utilized the power of a point theorem 3 total times. This previous one, we used it again at the beginning to get this value of 9, and then there was a little bit of a stretch here where we actually had to do some outside thinking, and the diagram wasn't set up super well, but we were still able to utilize the power of the point theorem in order to get our answer.